by way of a little background, and I'm going to start from some basics here and then just jump right into stuff and then do some examples. What are contours? Contours are like just about anything. It's where we're trying to fit a square peg in a round hole. It is a two-dimensional representation, you're looking down from a plan view, of a three-dimensional object or surface. Think of it that way. I know you were told there'd be no math. There is a little math later on, but it's math you can do with your spreadsheets anyway. Stop and think about, 1 point of data gives you a point in space. 2 points will define a line, right? 3 points gives you a plane. And then more than 3 points, you can start to define a surface where that's not just a planar feature. Obviously, the more data points you have for this thing that you're trying to map in the subsurface that you can't see, the better, to a degree. Sometimes it could make things a little more confusing. But basically, this concept here is just why do I need 3 points at a minimum to try to define which way the groundwater slopes? And that's what the contours are, the representation of that slope. Some things that the contours can tell us. I mean, the most obvious one that we always try to figure out is which way does the groundwater go, and with the groundwater, the contaminant transport. But there's a lot of other things. If the data set is amenable to, you can read in and see some things, like preferential flow pathways. Is there a reason that the groundwater goes a certain way that doesn't seem to jive with, the simple understanding of heading from higher ground to lower ground? That's where you get your hydraulic gradient for your transport and velocity calculations you're going to do. The hydraulic gradient is just the distance and the head drop over that thing. We'll see that as we go through. Sometimes you can see the interaction with surface water bodies if you have the right monitoring set. Sometimes you can actually see that it doesn't interact with the surface water body, which is kind of interesting if that was your conceptual site model presumption. And this one I don't have an example for later on, unfortunately, but it is, you can actually sometimes see a change in the subsurface lithology. Basically, if you go from a very highly permeable material to a low permeable material, the water's going to back up essentially kind of behind a dam. So it'll be flat and then very steep when it gets into the lower permeability material. Again, most of these things you have to get lucky to find out. With the kind of work we do, where we're putting wells next to areas of concern, maybe we get one up gradient or two to help define us. Sometimes our geometry is difficult. And the example that we're going to work through later is about as simple as it gets. In fact, it's more simple than I thought it was when I got into it. Now I'll show you why. It's almost embarrassing, but it's a real life. So I like to do that. And there are multiple ways of doing contours. I'm an old guy. I'm old school. I learned to do it the hard way. It's actually pretty easy, and that we'll work through an example of that. Basically, there's a number of software programs that are fully capable and getting better all the time. And I believe we'll be eventually moving to the Rockware system, which I have used on occasion in the past and find it very, very good for this kind of work. And then, of course, just give it all to Bubba, right? But there's a note under that, and it's that to remember to check before and afterwards, because Bubba will take the data and do with the data what the program does to the data, but he doesn't know if the data is right coming in. He doesn't know if it's right coming out. That's your job. So I'll reiterate that a couple of times in the talk, just make sure that you proof the data before it goes in so he doesn't waste his time and yours and our budgets. And then when the stuff comes out, there's some things to look for. We're going to do manual contouring. And like I said, this is old school. You got your map that has your wells on it, your calculator, you got your engineer's scale and a pencil, and that's all you need. So let's say you finish drilling on a Friday and you're really curious about what's going on, and you've got, field services came in and sampled on Friday for you and sent you a copy of the field notes in a timely manner, and you've got them, and I want to know which way this goes. And you got 4 or 5 wells out there, so it just makes sense to be able to do this. So this is a very simple site. This is up in Winstead. It has 5 wells on it, 4 down gradient along the river, and 1 up gradient in the center of the site. A pet peeve of mine, and I think everyone should try to stick to it as much as possible, is to stay within what I call the domain. So the domain on here is that red line. The red line is connecting the wells. So as soon as you get outside of that realm, that domain, you're speculating. The farther you go, the more speculation. One of the problems with the old computer contouring programs was like nature, they abhorred a vacuum. And they would try to fill all the empty space with information. So, your domain there was a square that might have had 3 or 4 wells in it somewhere, but it would fill the whole space. And you had to figure out what was good and what was bad. They've gotten a lot better. The algorithms they use to do the solutions are a lot better. So things work better than they used to, and they're improving all the time. But what we're doing here today is just a literal interpolation. And not consequentially there, that it defines basically a triangle because all the wells are in a row along the river. Probably not a great mystery here as to which way the groundwater is going to go on this site, even without knowing what the topography is on it. We'll just say that the parking area next to where MW1 is the elevated spot on the site. So yeah, it's not only got the river bounding it, but topographically it goes to the river. So this was basically a no-brainer when you got there, where it was up and down gradient. Zooming in here. So I defined the domain where I can work in. I've put in blue, the groundwater elevations that we calculated after the survey and the groundwater measurements were done. Those got checked before they went onto the map. I'll reiterate that a few times. So we're looking at the data set, determine what the highest elevation we have on the site is and the lowest. And somewhere in between there is where our contours are going to be, because that's the beginning and end of our data set. In this case, the highest was 99.09 at MW1, which was out in the parking lot area. And then down along the river, MW2 was the lowest at 95.15. These will come in handy as we think about this. So you look at that, you've got something a little more than 99 and stuff that's a little less than 96. And for a site like this, 4 1-foot contours would give you, a real nice spacing in here. How many contours you need and what the spacing depends on the data set. You get out in some areas where the groundwater is flat as a pancake, you might be, contouring to the 100th. In this case, it's an easy one, about 4+ feet of relief in the water table between the upgradient well and the downgradient ones by the river. So next to the outside red, just for representation, I put the distance along from monitor well 1 to monitor well 2, and the distance from monitor well 1 to monitor well 5. In this case, I didn't do the intervening ones because they are all under 96, plus or minus a few. I'm not going to gain anything by that. So as it turns out, I only needed to do 2 calculation lines here to do my groundwater contours. Oddly enough, when I measured the distance from MW1 to 2 and 1 to 5 with my scale, it's the same distance. So it's getting even easier. And I did not know that until I was actually making these up. So it happens. Now here's the big calculations, right? So on the left, you'll see elevation high, elevation low. That's between MW1 and 2, and then on the bottom of that is between MW1 and MW5. And you get the differential in feet. So there's 3.9 and 3.52 are the head differentials between the monitoring wells. For MW1, it drops 3.9 feet to MW2. So we've got the head differential between the two wells, and we've got the distance. Now you recall when I did the map, I put 5.3. The distance when you're doing the gradient calculation, so long as it's consistently measured, it really doesn't matter what the units are. And I'm not going to go into that to confuse it. But if you have a map scale and you want to use your scale to scale, that's fine. You don't need to. So I measured 5.3 inches between the two wells on the copy of the map I had. I changed that to 53 because it's inconsequential and it looks better in the calculation. So the distance between 53 divided by 3.9 is 13.58769, and 53 divided by 3.52 is 15.05682. Obviously, I actually did these on my calculator and did all this on my calculator and then put it into Excel for presentation purposes, because you can't see my calculator. And also as a double check that I didn't mess up the math and somebody would catch me on it. So that's the left-hand block. So what we've done there is define the gradient. That's the slope. It's on this scale, if that 53 was feet, then it's 13.5 whatever feet per 100. We said we were going to make 4 groundwater contours. So from 9009 to 95 something, we need to know where the 99 is, the 98, the 97, and the 96. Those are the 4, it's as easy as it gets, 4 full 1 foot contour intervals. And all you do is you start with the elevation from one end to the other on the line, doesn't matter. I like to subtract. I started with 9109. So the 90-foot contour is going to be 0.09 difference from there. And then as we go each foot, 1.09, 2.09, 3.09. Now to scale those, we have to then multiply it by the gradient. And that's what the bottom line is. So for MW1, MW2, 0.09 times 13.58 comes out to be like 1.22, which you would expect. It's like right on top of MW1. And so on down the line. I did it for both of these lines. They're slightly different because the gradient's slightly different, but they're the same length and the head change is a little different. Does anybody see where this is going? If I missed a step in here, does this make sense? But basically, I'm multiplying that distance that I want it to be at, that head that I want it to be at, by the gradient, and that gives me the distance out from my starting point. So when I do that, and then I actually yellowed these in so they're almost visible, but you can see where the yellow highlighted groundwater contours actually fall in relation to where the monitoring wells are. And you can actually see what I did is I went out each of those lines, that specified difference, and made a tick mark. Went out the next one for the next foot contour interval, made tick marks on each one, and then just played connect the dots. So this is about as easy as it gets. I can't believe that I started this talk out with this easy one, but I was all the way down the line when I realized this is stupidly easy. Anyway, it's probably better to start with something simple. Now, if you have more than the wells I have here, or the geometry is different, you do this same exercise of the point to the next point to the next point, and just draw the line, do the gradient between them, scale out the distance, make a point. If you have more than about 5 or 6 wells, this gets to be a little time consuming. But it can be done if you don't have access to the software, you're somewhere, and you want to try to figure it out. I'm going to get into some of the bugaboos now. That's all the math, by the way, and you can extend that system to any number of wells that I give you. So common sources of error in groundwater contouring. Every time you handle data, you write it down in the field book, you type it into the table to give to Bubba to contour. Bubba types it into the machine. Every time it gets touched is a possibility for error. And that tends to be where we typically see. That's the first thing you go to when something looks wonky. Go back and check the data set. And it's not because everybody has bad handwriting. It's just people are in a hurry. They're following down a line and they go to the wrong line. They do the tab instead of the ground. There's things like that can happen. Going to the Equus Collect, where the data is taken and entered, once everything is interoperable, should really cut down on those issues. One thing we run into time to time is people aren't taking the time, or we're working with maps that somebody else made where the wells really aren't where they say they are on the map. Always something to check, particularly when you're out there. Map makes it look like it's about 5 feet off the building and it's 25. That can move that whole point over. And on a flat water table area, that can be really significant in your interpretation of the water flow. So things to pay attention to. I've done it. I've misread the water level indicator. I pull the thing up and I think it says 7 and it's actually at an 8 or 9 or something. That one's almost impossible to catch because it's taken, it's recorded, and it's done. I got into the habit years ago of doing it 3 times when I take a water level, and it better come out basically the same each time, or I throw out the one that doesn't. If it comes out differently all 3 times, I just go and drink. Maybe that's the problem. Some of the other things problematic are mixing well types. So I've seen people, there's shallow and deep overburden wells, and they're trying to contour them both into the same data set. Sometimes it's all you got to work with. It'll give you something. It's better than nothing. But if you can avoid it, don't do it. Similarly, don't mix overburden and bedrock wells. Things happen very differently in those media. And again, sometimes that's all you got to go with. Sometimes the overburdened water goes away and all you've got is a rock well. And that's your first water. It's justifiable to use at that point. But if you can avoid it, I would rather draw an overburden map separately that doesn't go into the area where the bedrock is higher than the water table. And if I have the data, draw a separate map for the bedrock wells, if there's enough to make it worthwhile. Something else that happens, and it's endemic in our industry because we're all inherently lazy, guilty. But things get carried over. You forget to take something off a figure or out of a table, or you type over a table because you don't want to reinvent the wheel every time. But it is one of the spots where we can get errors happening, is that stuff gets carried over. It might even just be that, like when the map gets redone, one of the wells still has, last quarter's groundwater data, the number, even though the contours are right. And then it doesn't match up. So we'll go through some tricks about how to catch things. This is a site that we'll start with. I'm not sure whose notes those are. I think they might be Keith's, yeah. But this is not, the person who's going to get beat up on this doesn't work here anymore. And you know who it is. This is one of the things, the data got collected. It's up in New Hampshire, by the way. The data got collected, and someone else who was to work here, got a hold of the field notes and looked at the data, and I'm not going to go into the nasty bits. Looked at the data and said, it is way different over there. Because what he had done, at the start of the column here where it says HRP 10, he saw this 51.16 as 57.16. Changed the water table by 6 feet. Now, this is the actual cartoon that was sent to me, look. Well, this is a sand aquifer that goes on for miles. there's no way, short of having, a pumping well right there, to get the water table to either draw down 6 feet or come up 6 feet. And the person who drew this should have known that right off the bat. But these are the kind of things that, are the oddities that you really need to pay attention for. This one is very easy. By the way, the examples I'm using are either sites that are mine, were mine, or I've been called in and worked on. If you guys have any interesting examples of stuff that you either need help with, or I could just use as other examples as the process here, matures, I'd appreciate them. So this I can't say enough. Check and double check your data and your maps. So, did you proof the data set before you handed it in to get it contoured? Did you get back from the contouring what you expected to see? Like, I thought it was going to go that way, and it seems to be going that way. That might be that there's an error or something. Might not be. A lot of these sites we map, we sample quarterly, for in some cases decades. So you've got 20 maps that have been created over the years. Does the map you got now, the one you did or you had done for you, look like the other ones? Plus or minus a little bit of seasonal wobbling and things that might have gone on over the years. Are the elevations on the map correct? Because like I said, sometimes they don't get changed. And are the wells on the correct side of the contours? I see this sometimes because people are trying to fit a contour in, and a well that's 90.09 is on the down gradient side of the 90 contour. They're just simple little things. QA/QC check. All the data seems good. If it looks wonky, maybe there's something else actually going on here. I put this, I didn't know where to put this. This is like, I almost called this my list of pet peeves. Extending the contours outside the data set. There's really not very many times that that's necessary. Sometimes for like a conceptual model, but not for an actual, groundwater flow map. So like if you're doing a conceptual model that things aren't really to scale perfectly, yeah, you can show that, oh, here's the gradient going that way and everything here moves in that direction. But try to avoid that. If you have to go for outside your comfort zone of the data set, dash them. Particularly if you go like beyond your data set, like in the down gradient or up gradient direction where you really have no data. Extending them laterally a little bit is a little more justified, because you do have a line trend there. Oh, here's another one. Just because the program that you use gives you a lot of contours, you don't need to use them all. Sometimes they'll cover up all the other features because it's about picking because a lot of programs have a default number of contours they'll try to put in regardless of, the slope of the head differential in the water table. Odd results. This was one that was brought to me a little while ago, later last year, not earlier. And it was brought to me for a different reason. It was about doing a alternative surface water protection criteria. But I got copies of the maps, and there's the better part of 2.5, maybe 3 years of data on this site, mostly quarterly monitoring. And almost all the time it looks just like this, simple progression going across the site. Makes sense with the topography, makes sense with where the river is and stuff like that. But every so often, maybe every third, fourth, fifth monitoring event, you get this. And this has happened multiple times now. You got one well down here in the, I think that's north to the top, so we'll call it the southwest corner. That's 4 feet higher than everybody else. And the rest of the wells are all still at that same plus or minus a foot or so of the elevation that they show all year round. So naturally we thought, first there's a transcription error, but no, it's happening multiple times. We went back and looked at the survey data, looked at the well construction. Still don't have an answer on this one, but it's real. It actually happens. One of the things that we're looking into is you'll see the square there, which is a shed building, and kind of almost under it was a former septic system. One, we think maybe when they hooked to the sewer in '89, they didn't abandon the septic properly, and it might still be hooked up to something. And we're seeing, stormwater or something getting into that system. The other thing is that out on the edge of the road is the stormwater system, and this is along Trout Brook, which has got flood control, so the stormwater has to get pumped up and out. And maybe we're just seeing the times when the pump system is either down or overtaxed. And so it's backing up in the stormwater system and infiltrating out into the aquifer. But the first time you saw this, you'd go, somebody screwed up. And they didn't. Everybody did what they were supposed to do. The data's immaculate. This is a site in Pennsylvania, and this is about surface water interaction. And then I put in not. So the original conceptual site model for this site was, you can see the contours there in the blue, heading right towards the river. That river is almost like the size of the Farmington out here for scale. The site itself, which is about where most of those contours are, is 21 acres. It's a good size area here. And the model was, it's going to the river, tested the river, we're getting part per billion levels in the river of chlorinated solvents. It's like, oh, yep, complete model, complete pathway. Now, all these rocks are actually in bedrock, or these wells are in bedrock. And even though this is the shallow rock, it's going right under the river. The river is actually perched on about 30 to 40 feet of glacial lake clays, so right near the glacial boundary in Pennsylvania. And so it went right under, and you'll see there's some orange monitoring wells on the far bank of the river there. Those were because you can almost see just off the edge of this here in the southeast corner, there were actually some domestic supply wells over there, and they had been impacted by this plume. So we had what looked like a perfect model going in. Goes right to the river, it's in the river. Turns out the stuff that was in the river was coming from 3 miles upstream from a completely different site. So just when you think you got it. And this is my favorite slide of all time. You may have noticed on that last slide that the groundwater contours were they're going towards the river, but they also seem to be like peeking up towards the northeast there. I should have pointed that out, I apologize. Just to the east of this site is a limestone quarry. This is about 200 feet deep down in it. And what you're seeing in the wall there is actually a karst conduit flowing at many hundreds of gallons a minute, 24/7. And it's still flowing today, but it's underwater because the quarry flooded. I just love that shot, and I got to work it into every talk I do. Preferential flow pathways. These are really hard to see, and I apologize, but I did make this one. This is a site I've been working on off and on since around 2000. And I did the first phase 2 down there. And this was our interpretation. It's Branford, right on the river. The bottom of the picture there is railroad tracks, and then a little bit of shoreline, and then the river. And we're doing some work out there even now. We're probably going out there next week. But this is a huge manufacturing site. I got there when all the buildings were there. There was very little place we could get to. We put in our monitoring wells. And you probably can't see this until you really look at the things that I've included. But basically from near the center of the site, we have contours going east and west out from the center with the well array that we had at the time. And I'll explain why it does that in a minute. So we had worked for somebody, they went to jail, had nothing to do with us. It went into receivership. Next guy bought it, and he hired. This just give you an idea of the breakdown there. You can see the area in the center there is where the buildings were. That's all been demoed, and you can see how close we are, right on top of the river. Your natural thought, like my simple sight, is like, oh, it's right to the river. But I mapped it, and it went sideways. Next consultant came in. Now he's got a different set of wells. They put in other wells. They lost some of ours. They couldn't get to some or whatever. When they mapped it, you really can't see here very well, unfortunately. I should have doctored these up so they could be more visible. But he's got the groundwater going from the center of the site northeast, away from the river, and basically not coincident with what I had. Lastly, and this is a hand drawing by the current consultant, and they went through all the old data and made some data sets, and here they've got it going towards the river, towards the west, towards the northeast, and then back from the northeast into a saddle. This actually went into the DEP. What's really happening out there, in my opinion? So, the railroad track was built across the wetland, which means they excavated out most of the material was there, filled it all in with low permeability stuff, compacted it. The railroad track's probably been there for 150, 200 years, 150. Low permeability zone. At the western extreme of the developed portion of the site, and then at the southeastern, where I kind of had groundwater going to originally back 20 some odd years ago, there are drainage pipes going under the tracks with porous backfill and then into the river. And what I'm seeing is, and what the groundwater contours and the contaminant transport is telling me, that it's going not directly at the river, but it's finding its way around the edges. You're going to run into sites that have been impacted by petroleum. We use that acronym, LNAPL, light non-aqueous phase liquid. So this little chart here is something I stole from EPA. And it basically gives for several chemicals the specific gravities. These are things that are lighter than water, your typical things, gasolines and oils. A few of the solvents and things that we do work with on occasion at sites. If you've got floating product, we always used to call it, got LNAPL on your site, it skews the water table that you're measuring. So what you'll get back from field services, or you measure yourself with a probe, is that you'll have a depth to that floating material, that floating product, and then a depth to water. The floating product is lighter than the water, which is why it's floating. It will depress the water table proportional to its differential specific gravity. So that's the first column, is the density in grams per cubic centimeter. That's since you're comparing it to 1, which is water, that's the specific gravity of the material. If you multiply the thickness of that layer by its specific gravity, which is going to be somewhere, as you can see in here, between like 7 and 9, it'll lessen that apparent thickness. You'll add that to the groundwater elevation that you measured, and that will give you a relative groundwater, I don't want to call it relative, a comparative elevation where the groundwater would have been if the LNAPL were not present. And then you can use that well to help do your contouring. A lot of people, when they get a lot of free phase, they don't use those wells for sampling, which is good, but a lot of times they don't use them for the groundwater contouring. If you get enough wells and you don't need them, that's fine. I'm going to close. Thanks everybody for coming and participating. Feedback, please, either on this presentation or other topics, or just this topic in general. If you ever have specific questions on a project, just come see me. I'll more than happy to help. In fact, I much rather do that because it's more interesting than the stuff I have to do on my own. So please distract me. And again, if you run across anything that's interesting or puzzling, even if you figured it out, or especially if you figured it out, Those are cool examples to have for future stuff. Thanks everybody for coming on and putting up with me for this time. Bye-bye.